We've already talked about Q, the reaction quotient, in class. So this video is going to review when we use Q, and how do we tell when we use Q instead of K, the equilibrium constant. We're going to look at what Q tells us, and then I'm going to do 2 example problems where we are using Q. So first off, when do we use Q? What's going to be different about problems where we use reaction quotient instead of the equilibrium constant is that the first thing we're looking for is that concentrations given, this could also be pressures given, so concentrations or pressures, you know what, it would sound better if I said given concentrations or pressures. So given concentrations or pressures are initial, and we don't know if the reaction is at equilibrium or not. So now sometimes, if you think about the previous video, we had initial concentrations. We were not given equilibrium concentrations, but we had an equilibrium constant, and we were told to determine equilibrium concentrations. What's different about using Q is we're often asked the direction of the shift. So we're asked the direction of the shift. And I need to finish the second one. Sorry, don't know if the reaction is at equilibrium. So it becomes, Q becomes a predictor of the direction the reaction is going to shift to reach equilibrium. So if we're asked to tell which direction the equilibrium shifts, then we know that. I want to go back and talk about the given concentrations or pressures. This would be all of them. So there's no zero. So remember how if we had a zero, we knew that the reaction shifted toward the zero, so the side with zero increased? We don't know because they're all given. So that's the other way that we tell that we're using Q. Okay, so once we've used Q, what does Q actually tell us? And there's 3 situations. We have one where Q is greater than K. We have a situation where Q is less than K. And then we can have a situation where Q is equal to K. So 3 different situations. What we want to do is Q. We always want to write Q first because that's our predictor. And then we're going to compare that to our given equilibrium constant. So if Q is greater than K, well, let me start with the easy one. Let me start with Q is equal to K. This tells us that the system is at equilibrium, and if it's at equilibrium, then there is no shift. Now that means that your rates in both directions are equal. This is kind of rare. It's not as frequent as the other 2, but this can happen. If Q is greater than K, we have more products present. Now, one of the things that you can use to help you figure that out is remember that we're writing Q and K the same way. So if Q is larger than K, that tells us that we have greater concentrations or pressures in the numerator. So that means we have more products. So it's heavy on the product side. And the shift is going to be toward reactants. So the reaction shifts to make more reactants. Q is less than K, that means that we're denominator heavy. So we have more reactants. So the concentration or pressures of the reactants is greater. And so what will happen is that the reaction is going to shift to make more products. So just to recap that, if Q is equal to K, we're at equilibrium, there's no shift. In terms of doing math problems, if this is the situation, this last one that I'm talking about, you would just take the pressures or the concentrations that were given and you would substitute them into the expression and you would solve. Or actually, I guess you wouldn't be doing that because you'd be given K, so your answers would actually be your equilibrium concentrations. In this next example, where you've got Q being greater than K, you would then make your reactant side would increase and your product side would decrease on that change line. And I'm going to do examples of this, so don't worry. With Q being less than K, your reactant heavy, so the reaction is going to shift to make more products, and your product side would increase, so that would be a positive change. Your reactant side would decrease, the reactant side would be a negative change. So let's go on and let's do an example problem. So here we've got a reaction that's given. I'm going to go ahead and follow that same procedure we've been doing all the time. So I'm going to write the balanced equation first. PCl3 plus Cl2 in equilibrium with PCl5. I look, they're all gases. I'm given an equilibrium constant for pressures, and I've got a temperature. So I want my initial change equilibrium table, and I'm going to draw my fence under the arrow. The next thing I'm going to do is I'm going to write in what I am given. So PCl3, I have 0.50 atmospheres. Cl2, I have 0.50 atmospheres. And PCl5, I have 0.20 atmospheres. So now the question wants to know which way is the system going to shift to reach equilibrium, and then what are the equilibrium pressures. So we're solving for this line, this equilibrium line right here. What's different about the example problems that we've done before is typically we would have a zero, like our products would be zero or one of our reactants would be zero, so we'd know which direction it was going to shift. In this case, we don't know because we have values of for all of them. So what we want to do is we want to write Q. Remember that Q is written the same way that we write our equilibrium expression. So the pressure of PCl5 divided by the pressure of PCl3, whoops, I forgot a P there, times the pressure of Cl2. Sorry, I'm leaning. Let's go ahead and substitute our values. So 0.20 divided by, these two are the same, so I'm just going to do 0.50, and I'm going to square that. Then I do my math. Sorry, lost my calculator. So I have 0.2 divided by the quantity 0.5 squared, and I get 0.80. Oops. Okay, so now what we want to do is we are going to compare Q and K. So Q and K. Q is 0.80. K was given up here. It's 0.0870. So looking at those two, I see that K is much less than Q. So what that tells me is that because Q is greater than K, I have more products And what that means is that the reaction is going to shift to make more reactants, to relieve, I guess, the stress of more products. So that means that reactant side is going to go up. I'm going to make that plus. The product side is going to go down. That's going to be minus. Now, because I have no equilibrium values here, I'm going to make my change x. They all have coefficients of 1 because that's what I have in the balanced equation. So I end up with 0.50 plus x, 0.50 plus x, and 0.20 minus x. Now, this is just like solving problems before. So I would write the expression. I'm not going to go ahead and rewrite this again because K is written the same way. If on an exam you were asked to write the equilibrium expression, you would want to rewrite this, but you'd want Kp here. So my Kp is given. It's 0.0870. That is equal to 0.20 minus x divided by 0.50 plus x, and that is squared. Okay, we're going to have to do some work now. Okay, so I've gone ahead and I've factored this. Now I need to remember that this is like it's over 1. So I'm going to cross multiply 0.0870 times 0.25 gives us 0.02175 plus 0.0870x plus 0.0870x squared equals 0.20 minus x. Okay, what I want to do now is I want to combine like terms. So I am going to move both of these to this side. So I'm going to add x and I'm going to subtract 0.20. So 0.02175 minus 0.2 gives us, I'm going to rearrange this so it's a nice setup for the quadratic. So this is minus 0.17825 equals 0. Adding x, so this is 1.0870 x. Okay, now what I want to do, this is my A, this is my B, this is my C. I'm going to substitute those into the quadratic formula. So x is equal to opposite B, 1.0870 plus or minus the square root of B squared minus 4, oops, A 0.0870, C negative 0.17825. Notice I'm not doing significant figures yet. All divided by 2A, 0.0870. Let's see what we... Okay, so when I solved, I got x as 0.161 or a negative 6.75. We talked about how we're not going to use the negatives because that gives us a negative value for concentrations, which we can't have. So we're going to use this 0.161. If I go back to the previous slide, that 0.161, oops, sorry. I don't know why it's doing that. I'm going to substitute that into each of our equilibrium compounds. And then what I want to do is I want to rewrite it. So I'm going to go ahead and I'm going to erase our Q quickly. That'll give me room here. Whoops. Here we go. Okay. So the pressure of PCl3 is going to be equal to 0.50 plus 0.161. So that gives us 0.661. We can have 2 sig figs. So let's do 0.66 atmospheres. The pressure of chlorine will be the same thing. Could have done that on the same line, but I missed that. The pressure of PCl5 is going to be 0.20 minus 0.161. So with two, whoops, sorry. .039. So these are our equilibrium pressures. So if we look at what we were asked to do, we were asked to predict the direction the system would shift to reach equilibrium. So we did that. We compared Q to K. Q was larger than K, so that told us we had more products. So that meant the reaction was going to shift toward the reactant side. That meant that our change was positive on the reactant side, negative on the product side, and then we followed that same procedure that we've used in the past for other equilibrium problems. Okay, I've got one more example for you if you need it. If you don't need it, I don't know what happened to it. I've got to find it. Okay, I just found it. If you don't feel like you need to listen to this, I'd quit watching. If you do, this is another example for you. So we have an example given an equation. We've got a mixture in a 5-liter vessel, gives us moles, wants to know if the system is at equilibrium, and if not, which direction it will shift. So this one's going to be a little bit faster because we don't have to calculate all the equilibrium concentrations. So I'm going to start with a balanced equation. Let me make this a big screen. 2 NOBr, it's a gas, in equilibrium with 2 moles of NO, which is a gas, and 1 mole of bromine. I'm going to do initial change equilibrium, double line under the arrow for our fence. I'm going to substitute initial values. So 0.029 moles. I'm going to divide that by 5 liters. I've got 0.152 moles. I want to divide that by 5 liters. And then for bromine, I have 0.52 moles, and I want to divide that by 5 liters as well. I'm going to give myself a little bit more room here. I didn't do that when I started. Okay, so now what I want to do is I want to calculate what each of the initial concentrations are. So I've got 0.029 divided by 5. I've got 0.152 divided by 5, and I have 0.52 divided by 5. And I'm going to use a different color. Let's do blue. So I've got 0.0058 molar NOBr, 0.0304 molar NO, and 0.104 molar Br2. Okay, so looking at this, I don't know which way it's going to shift because I have concentrations of all three initially. So this meets the qualifications for using Q because I don't know the direction of the shift. Can't predict that because I don't have any zeros. I've been given all initial concentrations. I don't know if we're at equilibrium or not, and so Q is going to be that predictor, which is going to let us know which way the reaction is going to shift. So what I want to do is I want to write Q, and I'm going to erase these because in this example I'm not asked to find equilibrium concentrations. So Q, write it the same way as I would K. It's going to be equal to concentration of bromine times concentration of NO, and that's going to be squared because it has a coefficient of 2, divided by concentration of NOBr squared. So there's our expression. I'm going to substitute. My bromine is 0.104. My nitrogen monoxide is 0.0304. That will be squared. My nitrosyl bromide is 0.0058. That will also be squared. And then what I'm going to do is do my math. So 0.104 times 0.0304. I'm squaring that. and then I'm dividing that quantity by 0.0058, and that is also squared, and I get 2.857, so 2.856. I don't know why I changed it to that, because this was 7. I think I meant 2.86. Okay, so now that I have Q calculated, what I want to do is I want to compare Q with K. And if I know Q is 2.86, and I look up at the information I'm given, and they said that is 0.215, in this example, once again, K is less than Q. So that means that we have more products that are present, and so what will happen is that the reaction will shift left. To make more reactants. This is in my way. Sorry, I didn't leave much room. I'm just going to do R for reactants. So we know that the reaction is going to shift in this direction. So if I were calculating this, the reactant side would be plus 2x, product side would be minus 2x, and minus x.